Well, good afternoon. I congratulate all of you for finding your way to the proper place on the proper day. For those of you that are physics faculty, this is one day early, and for those of you that are Saturday morning physics people, it's not on the weekend. So we have an excellent talk today, and it is in honor of Tao Wu, one of our distinguished graduates. So this is the 21st Tao Wu Distinguished Lecture in Physics. The Tao Wu Lectureship was endowed in 1991 by a generous gift from the University of Michigan Alumni Association in Taiwan as a permanent tribute to Dr. Tao Wu, one of our late distinguished alumni. In 1907, Tao Wu was born into a family of scholars in Canton, China. He received his PhD in 1933 from the University of Michigan under the direction of Samuel A. Gouchschmidt. His early work on heavy elements pointed to the existence of transuranic atoms. Those are atoms which have masses larger than that of uranium. He returned to China in 1934 to teach at Peking University. From 1949 to 1963, Dr. Wu directed the Theoretical Physics Division of the National Research Council of Canada. He was chair of the Department of Physics and Astronomy at SUNY Buffalo from 1966 to 1969. Dr. Wu was appointed director of the Institute of Physics of Academia Sinica in 1962, chairman of the National Science Council of the Republic of China in 1967, and chair of the Committee for Science Development of the National Security Council, Republic of China in 1967, a position he held for many years. He was also president of the Academia Sinica from 1983 to 1994. He had a wide and varied career. Under Dr. Wu's leadership, the policy laid down by the National Science Council in 1967, as well as the revision of the science curricula and the rewriting of science textbooks in high schools, and the revitalization of the Academia Sinica, have made dramatic contributions to the development of science and technology in Taiwan. Tao Wu was deeply respected for his honesty, integrity, and moral courage. He has inspired 4 generations of physics students in pre-war Peking, post-war United States, and Taiwan. Among these students were Nobel Laureate C.N. Yang, who delivered this lecture in 1992, and T.D. Lee, our 1995 lecturer. Dr. Wu authored 20 books, including a 7-part series on theoretical physics and 7 volumes of collective essays. He published over 120 papers on a wide range of subjects in modern classical physics. In 1991, the University of Michigan conferred upon him an honorary degree, a Doctor of Sciences. The citation reads in part, "More than any other individual, Tao Wu was responsible for raising physics from its current level in both mainland China and Taiwan, and is chiefly for his extraordinary work as a teacher and scientific statesman that Dr. Wu has become known throughout the world." Commending his exceptional influence as a science teacher and policymaker, the university is proud to bestow upon Tao Wu this honorary degree, Doctor of Science. In 1994, Dr. Wu was awarded the Presidential Medal in Taiwan for his distinguished achievement. Dr. Wu passed away in 2000 in Taipei. So I'd now like to introduce Professor Tim Chup, who will tell us about our speaker for today. Tim?
Thank you, Brad. Well, it's my great honor to introduce Dr. David Wineland today, who is leader of the Ion Storage Group at NIST, which is the National Institute of Standards and Technology in Boulder, Colorado. As you know, Dave, along with Serge Haroche, is a 2012 Nobel Laureate in Physics, recognized for work on atoms as fundamental quantum systems, and we'll learn more about that today. Dave's very busy these days. Everyone wants him to visit, wants him to give talks, and wants to show Dave what they're doing in their work. So we're really very fortunate and very grateful that you've come to visit Michigan, Dave. And we've kept Dave very busy. In addition to this lecture, he's met with faculty, researchers, and also separate groups of graduate and undergraduate students. This is particularly valuable for our students and their educations, and we want you to know, Dave, how much we appreciate your efforts. Dave grew up in Sacramento and attended UC Berkeley as an undergrad during quite a tumultuous time, the free speech movement as it emerged. He was quite taken with literature originally and planned to major in English, but fortunately physics took over. After Berkeley, he moved on to graduate study at Harvard, where he worked with Norman Ramsey. His dissertation topic was experimental atomic physics, realizing and then making measurements with the deuterium maser. Like Norman, who worked under I.I. Rabi, Dave got deuterium. heavy hydrogen, and in addition to surmounting the new technical challenges, he made innovative tests of fundamental principles based on the structure of deuterium, which is a spin-1 object. From Harvard, Dave moved to the University of Washington in 1970 to work as a postdoc with Hans Dehmelt on charged particle and ion trap techniques, and in 1975 he moved to Boulder to join the time and frequency division of what was then NBS, the National Bureau of Standards, and is now NIST. At NBS, Dave started a new group, the Ion Storage Group, to develop, among other things, atomic clocks using the transitions or vibrations of charged atomic ions. This work is extremely technically challenging, and Dave put together an awesome group of scientists and led the work that steadily accomplished many firsts in laser atomic physics. One very notable first was effective laser cooling of atoms, which in a way launched what is currently the most active field in atomic physics, and led to 2 earlier Nobel Prizes on laser cooling and Bose-Einstein condensation. Laser-cooled and trapped atoms have provided a remarkable system for many amazing accomplishments by Dave and his colleagues, from making crystals of ions to studies of fundamental laws of physics to quantum computing. The next and upcoming most active field, I think, in atomic physics. And Dave's work has effectively helped launch this field as well. In addition to these many contributions to research, Dave is widely admired as a mentor of so many of those who make up the current core of atomic physicists. There has been no greater marker of success in AMO physics in recent decades than a postdoc with Dave. And I hope many of you noted a letter that was in January Physics Today by David Kelpinski, a PhD student under Dave, who relates Dave's amazing talent for guiding his team towards success while valuing each individual's talent and contributions. This role as mentor to so many successful scientists is very much like the role that Norman Ramsey played for an earlier generation of atomic physicists, and this has played a huge role in the development of a thriving field. Dave has, of course, received numerous additional awards to the Nobel Prize that recognize his work, including the National Medal of Science and almost every national award in laser and atomic physics. He's clearly a great scientist, he's a great mentor, and he's really a remarkable person. And Dave, we're very glad that you're here. Welcome. Thank you for coming, and we look forward to your talk.
Well, thanks, Tim, for the nice introduction. It's a pleasure to be here. I've known Tim and a few others in the physics faculty here for almost my whole career, so it's nice to return here. I feel a little unfortunate. I have to give this talk on your day of mourning after the basketball game, but I know Michigan's got a young team, and it was really an exciting game. Although I have to admit, I went to sleep after the first half, or I missed that. The other thing I want to say is that I think certainly probably many of you here because of the prize this last year, and I think both Serge Hirosh and I feel that certainly in our case that it's of course very flattering to have received this award, but I think we both feel it's more a reflection of our field, and that there's many people who could have gotten the award besides us. So anyway, so I think we're more representing the field rather than individual accomplishment. So let me start out with the part of the title. One of the things that makes this subject interesting was that one of the founding fathers of quantum mechanics, Erwin Schrodinger, he came up with the basic theory along with some other people that this theory of quantum mechanics. And what's always amazing to me is, it's been extremely successful, and he had the courage to point out early on some of the problems that he perceived with the theory. And the basic problem is that we have this wonderful theory of quantum mechanics, but by itself, all it predicts are these continuous evolutions of systems. And the way he expressed his concern about this apparent problem with the theory was that early on, the people like Schrodinger, Einstein, Bohr, they had these, they would discuss the implications of quantum mechanics, and they tended to think about small particles, a small number of particles to describe the behavior of quantum mechanics. But so Schrodinger just expressed his dissatisfaction with the consequences of the theory by the following example. So he cooked up this example where you have a single radioactive particle and then some mechanism that if the particle decays, it releases poison and kills the cat. Now, in principle, or rather in practice, we can't write down the equations for this, but in principle we can, and all quantum mechanics tells us is that after a time equal to the so-called half-life of the particle, the system, which we often we describe with these symbols here, but if you're not a quantum mechanic, don't worry about that. But the key thing is that quantum mechanics tells us that the system after this half-life, 50% probability of the particle decaying, all quantum mechanics tells us is that the system in the box is what he called the superposition of the particle undecayed and the cat alive, and the particle decayed and the cat dead. Not one or the other, but both at the same time. So just to give for the non-quantum mechanics out there, I think a nice analog to superposition, which I like, was presented in this book down here, is the following. If you play along with this kind of optical, not an optical illusion, but if you think about this box up here, and in its form up here, you can, if you play with your eyes, you can sometimes see this surface here be in the foreground, and other times this other surface be in the foreground, these two cases down here. So this is like a superposition because it's not one or the other, it's actually both at the same time. And this kind of this ambiguity about which state the box is in possesses both properties simultaneously, very much like this superposition state that Schrodinger talked about. The other thing, another aspect of this example, which I like, is that if you look at the upper right-hand image and at some instant in time, let's say this face could be in the foreground, that's very much like measurement in a quantum system. We can prepare these superposition states, but when we measure them, they tend to jump to one condition or the other. So this is, I think, a good analogy to what we call collapse or projection into one of the states when we actually measure these systems. And I'm not going to say a lot about entanglement, but it's a key part in everything we deal with. And a simple example of that is if you'll again play along with this analogy, at least for me, when I tend to see, if I see this, say that this surface be in the foreground, then I tend to see this surface be in the foreground, much like this example down here. And this is very much like an entangled state. Before we measure it, it's not one or the other, it's both. But the entanglement part is that what we see in one box tends to be correlated with the other one. So this is very much like, so Schrodinger's example is an example of this entangled state where the property of the radioactive particle is correlated with the state of the cat being dead or alive. So this is kind of the notion of entangled states that we talk about. Well, as I say, Schrodinger was bothered by this, and many of us are still bothered by this, this idea of superposition, that it really should map onto more macroscopic situations. And so in the early 50s, he posed one way out of this problem. He said, well, maybe all these discussions we've been having with these simple microscopic systems, they're leading us astray, and to these consequences of a cat being dead or alive. And so his way out of it at that time was, he just said, well, we can't play with one electron atom or molecule. And we do in these thought experiments that we discuss, but that invariably leads to these ridiculous consequences, meaning at the macroscopic world, you could have a cat both dead and alive. Well, that argument doesn't work anymore, because in fact we can at least play with these small numbers of systems. And of course, this has taken a lot of technological development over the years, but certainly what we need precise control of these small systems. We need to, just like I didn't point out in the cat example, you need a sealed box around this cat on the radioactive particles so that the outside environment doesn't disturb the system. And we need fairly good isolation from the environment. And so far we can't play with anything really macroscopic, but we can exhibit all these properties that went into these early thought experiments. So what I'm going to, as the abstract indicated, I'm going to talk about my part in this story of this development of being able to play with this. But again, it's certainly involves the work of many people throughout the world over these several decades now. So my story is Tim already mentioned. I went to graduate school, and I was a student of Norman Ramsey. This is Norman here, and this is me trying to get close to the boss, you see. Anyway, at that time, this was not, when I joined the group, it was not very long after Norman and his close colleague Dan Kleppner had developed the hydrogen maser, which is like a laser, but in the microwave frequency range. And this device is still used. It's still a very useful form of atomic clock. In any case, so after this first invention and then the demonstration of the maser, of the hydrogen maser, Norman wanted to get a precise measurement of all of the so-called hyperfine frequencies, these microwave and RF transitions of the three isotopes. So I chose my project was to measure the deuterium hyperfine frequency, and so I like to point out this was the measured frequency of the so-called hyperfine transition, and I think I'm the only one in the universe that probably has this number memorized, because it was the result of my thesis. Probably more importantly was that I was certainly hooked on this business of precision measurement, atomic clocks, and so on. And certainly these experiments, we got into the world of trying to control the environment, that is, to reduce the perturbations on the measured frequency. And already at that time we were talking about superpositions of the two states involved in this so-called maser transition, and these superposition states would last on the order of 1 second in the maser. So at that time, after graduate school, I went on to work in Hans Demold's lab. And actually, I was first interested, Hans was doing spectroscopy of atomic ions, which first attracted me. But at that time, Hans wanted to wanted to work on an experiment that was towards a precise measurement of the magnetic moment of an electron. And in that experiment, after I went there, it became clear that it would be best to try to work with single electrons, just because the mutual perturbations of multiple electrons in this thing we call a trap. For those that, again, for the non-physicists, you can think about a group of electrons being like a marble in a bowl that rolls back and forth. And that's set up by this electrode structure that we confine the electrons with. So anyway, the way we'd measure the number of electrons in this case, for those familiar with electrical circuits, we make a very simple circuit here, and we drive the oscillations of think of the electrons or the marble in the bowl at their natural frequency, where they oscillate back and forth, and we can electrically drive a derive a signal which is proportional to the number of electrons in this trap. So the way, as I say, one of the goals was to try to get down to single electrons. I guess I already said this, that the motivation for this is that although it hadn't been done yet, the best precision could get if we could do the measurements on a single electron. And this is the kind of data that we could get. So in this particular example, we started with 7 electrons in this trap, and we drove it at a critical amplitude where occasionally one of the electrons would get enough energy to strike one of the electrodes in the trap and be lost. And in the classical picture, you can think about the marbles just rolling out of the bowl. And of course, the interesting case was when we got down to this last step, and then we could do further experiments with these single electrons. And this, although I didn't stay around for this work, Hans Stamel's group went on to make a really precise measurement of the electron magnetic moment. And actually, one thing that's connection with Michigan, both Professor Crane and Rich, who were professors here at Michigan when I was a graduate student, they had made some first precise measurements, and these were the measurements by Hans Stamelt were considerably more precise after that, based on these single electron experiments. And at the same, when I was still there as a graduate student, I was still interested in the spectroscopy, and we came up with some ideas about how to cool ions. And essentially at the same time, Ted Hench and Art Shallow, who were famous laser physicists, they came up with this idea, which at the time didn't look the same, but in fact the ideas are very much the same. And the reason this was important for spectroscopy is that the idea of cooling ions, what we call laser cooling, and basically we're just cooling down the kinetic energy of the ions or electrons in the trap. And this is important in spectroscopy for at least one of the primary applications would be then that we'd suppress time dilation shifts. And for the non-physicists there, that you may have heard of the so-called Einstein twin paradox. And the way it's usually couched is if you have a twin brother or sister and they go out on a fast-moving rocket ship that goes near the speed of light and returns, you can cook up a situation where when they return, they would have only aged 1 year and you will have aged 10 years. And this is, of course, that's at extreme conditions near the speed of light and so on. But this is a very real effect, and we have to worry about it in our atomic clocks. That the shift due to this time dilation effect is much smaller, but where it sets precisions now, we have to have the particles that are atoms or ions be at low temperature to suppress this so-called time dilation shift. So anyway, after my graduate work, or excuse me, my postdoc work with Hans Stamelt, I went on and to NIST, which was then called the National Bureau of Standards. And my first task was that when I first went there, there was a bit of pressure to get the cesium clock working, and cesium atom, the so-called hyperfine oscillation in cesium, is what sets the standard of the second, and still does. It's the oscillation of the cesium hyperfine transition when so many cycles evolve, about 9 billion and so many. That defines the unit of time, the second. Anyway, we didn't have an operating standard, so my first task was to help get a measurement of the second. But my boss at that time, I should say, the NBS at that time was, at least the time and frequency division where this work took place, was largely a service organization. We had the task of providing the second, the unit of time, and there was work on calibrating devices that people would send us. But my boss at that time, Helmut Helvig, had this vision that we should be doing more basic research. So fortunately, at that time, he was able to get us some money to pursue this idea of laser cooling, which would be important for future clocks. So one interesting story was that my postdoc advisor, Hans Steenmold, had gone to work with Peter Toshek, who was then in Heidelberg, and I knew he had gone there to work on this laser cooling idea. And I think what's curious, I knew he was there, but I had no idea where they were in their experiments. I'm almost certain they didn't know about our experiment. And what's interesting, actually, although you can see these papers came out very nearly at the same time, to be fair, if you look at the submission dates here, they were 1 day ahead of us in terms of the submission, so I guess you'd have to say they were the winners, but it's still surprising. It was almost this near coincidence in reporting these experiments when we really didn't know, had no knowledge of the other experiments. So in their experiment, they were able to see this cooling effect because when the ions were cooled with this, using these lasers, they could see that the lifetime of the ions would be in the trap. And in my case, following on what I had learned in Hans Steenmold's lab, we actually looked at the thermally induced currents rather than the driven currents as we did in the electron case. We looked at just the noise currents from the ions in the trap, and that actually gave a direct measure of temperature. So you can see in this particular example when the ions were first hot here, and then we cooled them down, and they would gradually thermalize back to room temperature. So anyway, this was our group in 1979, a little bit after these experiments, and anyway, this was our complete group at that time. This is the same guys not very long ago, and actually my colleagues Wayne Atano and Jim Berquist, they look pretty much the same, but these other guys here, I don't know whether you can make the connection after all this time. And certainly our group has gotten a lot bigger over the years, so this picture was just taken a little while here and a little while ago, but certainly so we've expanded into a lot of different things over the year. Well, coming back to this business about after doing the cooling, one of the things was, just as in the case of the electrons, if we wanted for various reasons, if we wanted to do high-resolution spectroscopy, make atomic clocks out of transition ions, it would be best we could suppress the so-called systematic areas, the environmental effects, best if we went to single ions. So see, these were some of the first experiments. In this case, again, Peter Toshek's group working with Steenmold, they clearly beat us on this one. So they made their experiments were on barium ions, and barium ions is one of the very few single ionized atoms where you can shine a laser on, you can actually see it. It's in the blue, and they took some pictures in their experiments. And actually, I've been in the labs. We don't work on barium ions, but I've been in labs where you can actually look through a modest magnifier, and you can look in and see a single atom, a single ion in this case, with your eye. It kind of looks like a faint star. And we did some experiments a little bit later where we kind of used the same technique of, in this case, we didn't drive the ions out. We had invoked some chemical process, but we could see these steps in the scattered light, which indicated the number of particles in the trap. So I'll tell you a little bit now about our experiments. And not long after that, we became interested in mercury ions, and I'll tell you why in just a second here. But so that what you kind of want to have in mind, we have this electrode structure which holds our single mercury ions. And there's what we call an allowed transition, where we can scatter light off this transition, and we can, in this case, the radiation is in the ultraviolet, so we can't see with our eye, but we can easily make a picture with a ultraviolet sensitive video camera. And this was also, then this allowed us to see the ions, and by tuning the laser appropriately. I haven't described laser cooling for you, but basically you want to tune the laser frequency a little bit below the transition frequency for this particular resonance on the ion. But anyway, one of the reasons we were attracted to mercury is, well, here's a picture that we made with this UV video camera. So one of the reasons we were interested in mercury was we were looking way ahead towards the future. We started this in 1981, but looking ahead towards the future, there was an interesting transition that could potentially use for an atomic clock. This particular transition of mercury has when the atom is excited to this particular excited state, it can stay up there 1/10 of a second, and which means that equivalently the frequencies over which the transition absorbs radiation is very narrow, on the order of a few hertz. And but the key thing I'll give for those people not familiar with atomic clocks, actually they're extremely simple, and I should be able to tell you how they work in 30 seconds here. It's really not that complicated. But what you can think of is that what we do is we apply radiation, which excites, in this energy level picture, excites the atom. And what you can think of it is that in this case, the electrons in the mercury ion, they vibrate. They have certain characteristic vibration frequencies, and all an atomic clock does is that we look for the condition where the radiation is absorbed with maximum probability. When we reach that condition, we know that the vibrations of the oscillator, in this case the laser that produced the radiation, they're in exact synchronism with the natural oscillations in the atom. And the way the way we can measure this condition when the atom absorbs maximally is actually pretty simple. So what we do is we first we prepare the atom in the lower energy state, and then we apply this clock radiation, and then what we do is we apply the clock radiation alternately with this detection radiation. And the idea is the following: if this radiation was asynchronous, if it was off resonance with the absorption in the ion, then when we turn on this laser, the ion would have remained in its ground state, and then we see fluorescence. On the other hand, if we're tuned into synchronism on this transition here, the atom gets promoted to this excited energy level, and then when we turn on this laser, there's no fluorescence, and the ion goes dark. And this is actually a pretty dramatic effect. This is when we look at the scattered light, and one of the nice things is when we scatter light on this so-called allowed transitions, the atom can scatter about 10 to the 8 photons per second. Now, when we only collect a very small fraction, much less than 1% of the scattered light, but it scatters so many photons that we can easily see the condition when the atom changes state. So again, when it's in the ground state, we see the fluorescence, and when it's in the excited state, the fluorescence almost goes to zero. This is just background light. And if we put a discriminator at this level here, we can essentially tell with 100% efficiency when the atom makes the transition. Now, so I kind of tried to describe the condition of how we synchronize the laser oscillations with the natural oscillations of the atom. To make a clock, then basically we just count the cycles of the oscillations in the laser. And this was part of the reason we didn't do this in 1981, because this was impossible at that time. And it was only in the last decade where Ted Hinch and Jan Hall received the Nobel Prize in part because they made a device, the so-called optical comb, which effectively allowed us to count cycles of this laser oscillator, which the oscillations are at about 1 billion times a second. Okay, you can imagine that's sort of tricky to do. But anyway, they solved that problem for us. So I'm just going to summarize some of the results. So after, as I say, we started this in 1981. Jim Berquist in our group was really the one who was the leader and carried this through. Just a couple of features here of this single ion atomic clock. First of all, the fact that we confine it, even though it's maybe oscillating back and forth, this marble in the bowl. On average, the velocity goes to 0. So on average, this so-called first-order Doppler shift, the normal Doppler shift that we're familiar with, that on average goes to 0. So that gets rid of that effect. As I mentioned, the laser cooling reduces this time dilation shift. In this experiment, we went we wanted high vacuum, so we made an apparatus that went to 4 Kelvin, and it wasn't. We actually, in this experiments, the environmental shifts, we wouldn't have a problem if we did this in an apparatus at room temperature. The problem was a little bit indirect. It turns out that even though this trap was in high vacuum at room temperature, there's always some background vapor of neutral mercury, and it turns out when the mercury ion would be promoted to this higher clock level, when it collided with a neutral mercury atom, it would radiatively associate and make a dimer, basically a molecule, when that killed the ion. And unfortunately, even though as much as we tried at room temperature, we could only get the vacuums down so that the ion would only stay around 10 minutes. And that was about as long as it would take us to get everything tuned up, and then the ion would go. So we went to 4 Kelvin primarily to get very good vacuum. Basically at 4 Kelvin, almost everything freezes out, maybe except for helium, and helium's not a problem. But from that, we could get very good vacuums. And in fact, the lifetime of our ions literally went from 10 minutes to 6 months in one case. So this was the main reason we went to 4 Kelvin. There's some other advantages that. Anyway, there's a lot of other things to consider. But anyway, in this, after many years, it took us till around 2006, but we finally reached the condition where the systematic uncertainty, and we always quote these fractionally, that is the frequency shift divided by the operating frequencies, because we can always shift the frequency. So that's the typical measure. And at this time, we got down to an uncertainty of about 7 parts and 17, 10 to the 17 in this experiment. And the significance of that, this was the first time that any clock had gone below the cesium accuracy expressed this way. And what's amazing to me is that the cesium beam clocks were first developed in the 50s. The cesium beam clock that measured this hyperfine frequency was adopted as the standard for the unit of time, the second, in the mid-60s. And for all this time up to 2006, it really was the best clock. It had the lowest so-called systematic uncertainties of any clock. So it was an amazingly good choice. Now we're faced with a condition, and jumping ahead a little bit, there's many clocks that are better than the cesium now, and there's no obvious winner. So I think cesium is going to be around a long time. And of course, I have to apologize because I've only talked about our experiments, but there's many experiments around the world using different ions. These are some of those, and for those that are interested, these other clocks are summarized in this paper here. So anyway, one of the things after we got down to the point of handling the transitions in single atoms, the so-called internal transitions that I've described to you in this atomic clock, was also a challenge, and there are reasons we wanted to get down to control the the quantized levels of motion. So if you come back to this analogy, classically we think of the marble rolling in the bowl. It's a form of a harmonic oscillator. We know, though, at the fine level, at the quantum level, we have to consider even our oscillating marble, or in our case, the atom. There's rather than you thinking of a continuous oscillation, there's energy level structure where there's a ladder of states which are separated in energy expressed as frequency by the oscillation frequency. Of course, one thing that made this hard was that the energy separations between the ground and first excited state of the motion are about 9 orders of magnitude smaller than this, so we needed a more precise way to control things. So anyway, what we did is, if we, again, going back to this atomic clock experiment, if we would sweep out the frequency of the laser that is used to drive this transition here, what we would see if the atoms were at some finite temperature, again, think of the marble rolling back and forth in the bowl. If you sit on the frame of reference of the ion, what you see is that the laser beam that's coming towards you, it's frequency modulated because of the first order Doppler effect. So in those conditions, we would see not only the central feature, which is the interesting one, but we'd also see what we call sidebands, or just frequency modulation sidebands. So in this, what I've tried to relate to in this sequence here is that what you call a carrier in frequency modulation spectrum it represents, in the quantum picture, it represents a case where an atom, let's say it starts in the n=2 level of this quantized harmonic oscillator. It represents a case where the internal state changes, but the emotional state stays the same. And then in the quantum picture, these sidebands, we say, and this is what we call the blue sideband, it's at higher frequency. On the quantum picture, it represents a case where the atom is promoted from in this case, this example, n=2 to n=3, and for the same tuning, it would go from n=1 to n=2, et cetera, because the energy levels are equally spaced. And then finally, the other, what we call the red sideband, is the case in the quantum picture where the motion quantum state is reduced by 1. Well, this is interesting because it provides a way for us to cool the motion of the ions down to the ground state, the quantum limited energy, the lowest energy of this harmonic oscillator. And the way it works is actually pretty simple. If you'll take into account one thing, and that is for the conditions we operate, we hold the ion strongly enough that we make this bowl that holds the marble stiff enough that it turns out when the atom emits a photon from this excited state, with high probability it does without changing the harmonic oscillator quantum number. And for the physicists out there, this is basically the Mossbauer effect, but now in the visible part of the spectrum rather than the gamma ray part of the spectrum. So the idea of the cooling is actually fairly simple. What we do is we tune a laser to this, what we call the red sideband, and when the atom is promoted, the quantum number is reduced by 1, and then when it decays, as I said, it'll decay down without changing the quantum number to a high degree. So in this overall absorption decay process, the motional quantum state is reduced by 1, and at that point it's very simple. We just leave this laser on for a little while, and the atom walks its way down this quantum levels and finally finds its way into the ground state. And in fact, so what you can think about at that point, this process stops because when we try to drive this transition again, there's no n equal -1 level for the atom to be driven to, so the process stops. And in fact, it turns out a nice way to tell how well we're doing. So this is the picture you saw before, and this is an expanded view of the red and the blue sideband. And what you see is there's now a big asymmetry in the absorption, and that just simply represents, to the degree this line, this feature is flat here, that just means we're perfectly in the ground state and we never see absorption. And in fact, but anyway, we can use this ratio of the sidebands to indicate that we're predominantly in the ground state when we do this, after we do this cooling. So let me come back to having these tools in mind. We could do an experiment that I'll try to convince you it's an analog to Schrödinger's cat, and it was the following. So let's assume we've done this laser cooling so that the atom is in its motional ground state. Classically, the marble sits at the bottom of the bowl, and I'm changing labels on here, but this could be, for example, the ground and excited state of this clock transition in mercury. So we prepare the atom in its internal ground state and its motional ground state. And then what we first do is we apply radiation at this frequency for a time that then creates a superposition state of the ground and first excited state. And then skipping over a lot of details, we can take other laser beams, and what we can do is we can arrange a situation where the forces applied by the fields from the laser beam, what they'll do is we can modulate them at the frequency of oscillation of the ion in the trap. And so what that causes the motion to be excited, but we can arrange these forces such that it only acts on what I'm calling the spin-up part of this superposition state. So we create this strange situation where now we've separated the positions of the ions correlated with what internal state they're in. And just to make the situation a little more symmetric, then what we did is we flipped the spins and we applied this force again such that we would, at some instant of time, our atomic marble would be on the left side of the bowl, and simultaneously on the right side of the bowl, correlated with the internal state. So the reason we're calling this a Schrödinger cat, it's obviously a very small one, but the reason we call it is because what we're making the connection we're making here is that what was the single radioactive particle in Schrödinger's example is the single radioactive, either being not decayed or decayed is replaced here by which atomic state the ion is in. And then the more macroscopic property is whether the marble is on the left side of the bowl or the right side of the bowl, and we're saying that's like Schrödinger's cat being dead or alive. Well, okay, so you might say, well, this is kind of a cheesy analogy because it's really still a pretty microscopic system, and in this first experiment we could only separate the wave packets associated with the size of the atom by about 10 by a distance about 10 times the wave packet size. And so you might say, well, you can't call this Schrödinger cat, but I think one of the interesting things is if you say it's too small, I mean, you might be more willing to call it like a Schrödinger cat if we could separate the two parts of the atom by some macroscopic distance that we could see. But if you say this size is not, you can't call it a Schrödinger cat, then you have to say where's the dividing line? Where does it become this more classical situation? And that's a problem that physicists were all stuck with. There's no way to decide where this dividing line might occur. So this issue continues to be a subject of debate in physics, and I think it's an interesting one. It'll go on for a long time. Okay, so what I advertised a bit more in my abstract was this idea of quantum information processing. And the reason I talked about this Schrodinger cat example again here, we were able to create this situation where our atom was on the left side of the trap and the right side of the trap at the same time. Where this comes into play, I'll give you an idea in just a second. But so anyway, these ideas of quantum information actually go back. One of the luminaries that people know about, Richard Feynman, a physicist in the early 80s, where his ideas came from, and some of the others, was that he was interested in his case simulating the interaction of many elementary particles in some more complicated particle. And what happens is, for the non-physicist, what happens is that this becomes, as the number of particles goes up, the resources you need, the memory and so on, and processing capability in a computer goes up exponentially with the number of particles. So on the order of 10 to 20 particles, you run out of steam. You just can't simulate these quantum systems. And so his idea was that maybe what you could do is map the problem of interest, say these interacting elementary particles, onto some other system which could simulate the action of the elementary particles. But so these ideas were floating around, but what really set the things on fire in the mid-1990s, Peter Shor, a computer theorist, showed that he came up with the idea that if you could make this quantum computer, which I'll try to give you at least a flavor for what we're talking about, if you could make this device, he came up with an algorithm which showed that you could efficiently factorize large numbers. And many of you may know, but for those that don't, basically all of our modern encryption systems, what provides security when you buy something with your credit card and protects national secrets, the systems, the encryption systems that are used could be cracked with a quantum computer, could be efficiently cracked. And so obviously the government is interested in this, and that's funded certainly a lot of the work in the US and other parts of the world as well. Anyway, the story is after this, we don't read computer journals, so another guy who read both physics and computer journals, Arthur Eckert, he came to a conference on atomic physics in Boulder in '94, and he told us about this idea. And at that time, well, anyway, I'll go on to this, what happened after that in a minute. But let me give you this. I can't describe a quantum computer for you in any depth at all, but for those that aren't familiar with it, I'll give you some idea of why this might be interesting. So again, we're going to think about superposition again. And here, again, I showed this example of the marble being on the left and right side of the bowl at the same time. What's interesting to think about for a computer is that we could take our internal states, say the two states I talked about in the clock for the mercury ion, and we could make what we call a qubit. So we could make a state that we could either put it in the ground state or the excited state. Sorry, I changed notation on you again. But we could either put it in one state or the other, and it would act like a classical bit. But we could put it also in a superposition state where it represents, in some sense, both the 0 and the 1 state at the same time. And the reason this gets interesting is how it scales as we increase the number of these quantum bits. So if we have a 3-bit register, classically that could represent a single number, say, for example, as 101. In this superposition sense, we could represent all the numbers in this 3-bit register from 000 up to 111. So this represents 8 possible numbers, or 2 to the 3. And so it's this exponential scaling. The memory size could go as 2 to the number of these quantum bits we have. And kind of a dramatic example of that is if we just had 300 bits, in a classical computer that might store about a line of text, but in this quantum superposition sense, we could store 2 to the 300 numbers, which is about 10 to the 90th in decimal notation, And that's more than all the elementary particles in the universe. So in other words, in some sense, we could have a memory with these 300 quantum bits that would store more information than if we took a classical computer with all the matter in the universe. That sounds pretty good. The other thing that's interesting when we, and it's true of actually Shor's algorithm is a fairly good example of this. In his algorithm, it's not quite this simple, but we can think of as you plug in, if you're trying to factorize the large number, meaning find the product of two numbers, which gives a larger number, basically you plug in make a superposition states which holds all the numbers from 0 up to the number you're trying to factorize. And then what happens is the operations we apply to this system, they actually operate on all these numbers at once. So in some sense there's this massive parallel processing that goes on. And I'll give you an idea of the kind of operations we do in just a second. But the thing we have to remember, it's like in the first cartoons I was showing, when we do a quantum measurement, we tend to collapse the system into one of these states. I only showed you two states in the cartoon examples. Here, the message is that we may have some huge superposition. When we do the measurement on the system, it collapses into one of these states. So the kind of algorithms, and certainly Peter Shor's was one where what happens is after he performs the algorithm, basically most of these coefficients that describe how much of this state exists, most of them turn out to be 0 after the computation. Not all, but it turns out that when you measure and collapse into one of these states, you can then use a classical algorithm to drive the factors of the larger number. So that was the key, one of the key issues in his experiment. So to give you an idea, again, I can't really describe all the interesting features, but in fact, the prescription we need is when we think about what we call a universal quantum computer, it's very similar to a classical computer. So it may not be the most efficient way to build a classical computer, but you could do essentially universal computation, all types of computation with just two gates. And one, say, for example, a bit flip gate and a 2-bit AND gate. You could do universal computation. As I say, this may not be, just using these two gates may not be the most efficient way, but you could do this universal computation. And we have the same principle in the quantum world. Rather than bit flips, we do want to do something a bit more complicated. For example, we generally call this rotation, but as an example of that, what you think we want to be able to do on single bits, we want to do operations where we change the 0 state into superposition of 0 plus 1, and similarly for the 1 state. And in fact, a gate we often talk about is very much can be done classically as well. I show the conditions of this so-called controlled NOT logic gate, where you can see that the first bit, which we call a control bit, if it's in the 1 state, then it changes the state of the other, it flips the other bit from this truth table. And we can make a classical gate that does this, of course, but the interesting part about it in the quantum world is this can work on superposition states. And it turns out this is invoking this gate on superpositions is what gives us these, entangled states. Anyway, coming back, after this meeting in Boulder, two theorists that were at this meeting, Ignacio Serac and Peter Zoller, who they're well known in atomic physics in part because they're very good theorists, but they also they keep tabs on what the experiments can do and what they can't do. They were certainly very familiar with the ion experiments. And anyway, what they came up with is the following idea, and just at least to give you the flavor of this. So let's suppose we have 5 ion qubits, and I won't describe how the trap works. What you can think about is what this electrode structure does is that it supplies this harmonic potential, and it does it in 3D. And what we do is we typically make the harmonic potential along this horizontal direction relatively weak to confining potential along the transverse directions to this horizontal axis. And what happens is when we cool the ions down, they all want to fall to the bottom of this harmonic well, but the Coulomb repulsion holds them apart into this linear array under these conditions. So their idea was the following: in the idealized version of what they proposed, let's suppose you can think of this 5-ion system as kind of like a pseudo-molecule. It has vibration modes just like a 5-atom molecule would. And along this particular direction of the horizontal direction, there's 5 modes corresponding to the 5 ions. The simplest one to think about is where the 5 ions are all oscillating back and forth in this external potential. Anyway, but the key part is that, let's suppose using the laser cooling to the ground state, suppose we could, within the quantum mechanical limit, suppose we could freeze out the motion. So we put all the modes of motion in the ground state. And then what we can think about is the ground and first excited state of one of these motional modes also as a qubit. And the reason that qubit is interesting is because it's shared amongst all the ions. So in this simple example I gave, you can see that if we make a superposition on the ground and first excited state, basically all the ions are participating in that. So the basic idea of their scheme was that if somehow we could take a laser beam, and if we focus it on one ion, and in general, each one of these ions is going to be in some superposition state. If we could first map this superposition state of the internal state of this ion onto this motional state superposition, then because that motional state is shared with all the ions, if we could somehow make a quantum gate between this motional qubit and the internal state of this ion here, then effectively by this mapping procedure, we've made a gate between this ion, the internal state of this ion and this ion. And the final step is then is that after doing that gate, we undo this first mapping step and put the atom back in its motional ground state. So that's sort of the flavor of what they proposed. So to give you an idea, it's a bit more complicated than what I'll explain here, but coming back to this idea of how we did the cooling, you can kind of get an idea how the logic works. So let's suppose we have, here's this could be our optical transition state. And again, we also have this, we're talking about the quantized modes of motion for this shared mode of all the ions. So we're going to isolate the ground and first excited state. So the way the logic works, that was the second part of this scheme by Serac and Zoller, is let's consider the case where either the motion qubit is either in the 0 state or the 1 state. So if it's let's suppose it's in the 1 state, what we can do is we can tune a laser which excites what I called the red sideband before. So if it's in the n=1 state, we can actually have it make this transition to the excited state. And so what that does is it flips the internal state of the qubit. And conversely, if it's in the n=0 state, if you'll recall, there's no level in the excited state for it to go to. So in that case, the logic is such that if it's in n=0, nothing happens to the qubit. So it's this sort of conditional dynamics, this controlled phase flip that is sort of the essence of the logic. And it is a bit more complicated than what I've said here, but this sort of conditional dynamics is the basis for all the logic gates in any of these systems. And at that time, Chris Monroe, who was on the faculty here, starting in around 2000, he was actually in our group from 1992 to 2000. And we were in the lucky position. Some of these ideas, after we had done this ground state cooling, we were thinking of ideas about how to manipulate the quantum states. And after, Serac and Zoller sent us a preprint of their paper, and we just were in the right position. So in a couple of months, we could demonstrate this logic element, this logic gate between the motion and the internal state, which was sort of the key part of their their scheme. So I just, very egocentric examples here of the kind of work that's going on. There's been a lot of demonstrations, simple algorithms that use these quantum gates. You can kind of think of them as like subroutines in a Fortran program or something. And so we and other groups have done a lot of these demonstrations, and our group, TD Lightfried, has been has guided several of these experiments. I come back to this idea of simulation that started with Feynman. There's several groups, Chris Monroe is one of them, and the idea here is to one of the quantum problems we could simulate is, suppose, for example, we're interested in the spin magnetic interactions of electrons in a solid, let's say. It turns out each one of this is a particular example by John Bollinger in our group. It's a different kind of trap, but in this trap, the ions can be trapped into a pancake in kind of a triangular lattice. And the simulation part comes in because what we can do is we can oscillate the motion of each one of these ions in a state-dependent way. And it's the electric dipoles of these ions, when interacting with each other, can simulate these magnetic spin-spin interactions in a solid. So at this point, there's many groups pursuing this. We're certainly not at the point where, or I should say, we're at the point where we can do simple simulations, but so far they're on small enough numbers that we can simulate them efficiently on a classical computer. But I think most of us feel, the factoring problem is extremely hard. And probably the first problems where we might actually contribute something to science in this simulation sense is in this simulation sense. So that's why we're hopeful that maybe with maybe 20 qubits or something, we'll actually discover something interesting. And Rainer Blatt's group, he's one of our stiffest competitors, and fortunately he's a good friend over many years. They've been able to do the most complicated things simply because they have the lowest errors in their gates. They use calcium ions. We use other kinds of ions in our experiments. And as I said, these are just a few examples, and there's many more groups. Just to give you an idea, this is the number of groups that I'm aware of throughout the world that are just doing these kinds of experiments with atomic ions. And there's, of course, many other physical platforms. One that's gained a lot of ground in the last decade is making quantum bits based on Josephson junction systems. And so there's other physical platforms, and this is just atomic ions, so you can get an idea of the amount of effort going on throughout the world on this problem of quantum computation. Let me give you just a little idea of what the lab is like. In fact, what dominates our lives are these laser systems. Unfortunately, for most atomic ions, and certainly the case in our lab, these optical transitions, because we've already moved one electron, it takes that much more energy to excite an electron. So most of the transitions are in the near or ultraviolet, or from typically around 200 to 400 nanometers. So we have visible light lasers, and then using nonlinear crystals, we have to convert the light to UV. So certainly the work is dominated by these laser system, and what we dare to call a quantum computer is this little tiny thing over in one corner of the lab in a vacuum system. To give you some idea of that, I showed this idealized picture of the electrodes. And again, I don't have time to go on the details, but what we can do is we can mimic this kind of macroscopic structure on a smaller scale using lithographic techniques. And the reason we want to go smaller is that basically the speed of these operations is proportional to the motional frequencies that I talked about. And say for given potentials that we apply to the electrodes, the frequencies of oscillation basically go up as this 1 over the dimensions to the second power. So that's why we want to go small. Our first steps in that direction, this maybe doesn't quite like this system up here, but we got to be small enough where we needed to use lithographic patterning. And this is an even smaller version where in this picture, which I showed on the very first view graph, you can see each one of these little tiny squares in this array is a place where we can hold one or a few ions. And the idea, what we have for scaling up, is to actually be able to move our ion qubits around in a structure like this. We call this a racetrack, because you can see it makes this kind of oval. But this could be, with these kind of wide junctions here, you can get the idea. We could scale this to a very large system. So this is the kind of path that we and other groups are trying to go down. And I just mentioned we started this kind of thing, but now it's being taken over by the real pros in this microfabrication, and these are some of the groups doing that. So let me come back to the clocks, and the reason I'm talking a lot about clocks, it may not be quite so apparent, but the problems we have to face in the lab with the clocks or the quantum computing are very much the same. And certainly in the time and frequency division, this has been a project that we've carried all along, certainly since I started there. And so this is an idea where we're going to use some of the simple ideas of quantum computing to help us with our clock experiments. So this is what I'm going to describe here as an experiment which is headed up by Till Rosenband, one of our newer members. And the idea here is it's very much like the Mercury system. One thing that's nice, as opposed to the 1/10 of a second lifetime in a Mercury, the aluminum ion here has an upper state lifetime about 20 seconds. So that means the frequencies over which the ion absorbs the radiation is even that much smaller. So one way we could detect it is just as we did in Mercury, and there is a transition which could be used. Unfortunately, it's at such a short wavelength that we just can't get lasers there at this time. So what we're doing is employing some very simple ideas from quantum computing. The idea here is that let's suppose we have our clock ion, this aluminum ion, and we put that in with a beryllium ion, and this is sort of like a diatomic molecule in the sense I described before. So what we can do in this experiment, in general, again, we do the experiment just like we did for Mercury. Start the ion in the ground state. We excite it up to we apply the radiation to try to excite this clock transition. In general, that means the ion is in some superposition. And then using these very simple ideas that Serac and Zoller described in their proposal, what we first do is we map this superposition state onto the motion superposition of the ground and first excited state of one of these motional modes. And that way we reverse the process, but onto magnesium ion, which turns out to be one of our favorite qubits, and we can easily detect which magnesium state the ion is. So this allows us to basically measure what's going on in aluminum by measuring what's going on in magnesium through this transfer process. So it turns out this is over the several years now, we've reached the condition where we have the extremely precise clock, and I won't go into all the environmental effects we have to worry about. Mostly it's due to the shifts on these transitions are due to electric and magnetic fields. Now, electric fields include a lot of things. It could be electric fields from the traps, or it could be electric fields that are experienced during collisions. But in any case, those things we have to worry about. So I'm only going to isolate about a couple of things that more observational effects, you might say. And these are the relativistic effects. So I've already talked about the first order Doppler shift, which goes proportional velocity, and then the time dilation shift, which goes as the square of the velocity. So one interesting thing, I lied to you earlier. I said, well, when we trap an ion in the trap, the average velocity goes to 0. But if our target is to get down to relative shifts of a part in 10 to the 18, and what that means is that that corresponds in terms of this first order Doppler shift of a velocity of about 0.3 nanometers per second, which is a pretty small velocity. And what we have to worry about in the lab is that we have the laser on one part of the table, and then on the other end of the table we have our trap and the ion. And one thing we have to worry about is just because of thermal changes in the room, the table is either contracting or expanding, and it's certainly doing at a velocity which is much faster than that. So actually what we do is we started this a long time ago, but we took a technique that's used in satellite ranging where a ground station can determine the velocity of the satellite receding from it, basically through the first order Doppler shift. What's done is simply to essentially send a signal out, reflect it off the spacecraft, and then you measure the frequency shift when it comes back. It has twice the Doppler shift, the first order Doppler shift, and you can correct for that. And we can do this, so we have to do this in our experiments. We have to do basically this ranging to get out the first order Doppler effect. I've already described it, or said that the second order Doppler shift, the time dilation shift, we suppress that with laser cooling. Anyway, when all is said and done, there's a whole host of things we have to worry. But we're now down about 10 times lower than we were with the Mercury experiment. And the name of the game is to of course, push it down even farther and farther. So one of the interesting things we have to worry about is also a theory of Einstein. It comes from Einstein's, in this case, theory of general relativity, and that is that what he theorized, and it's certainly an effect we have to worry about, is that time runs at different rates in different gravitational potentials, and given by this expression here. And on the surface of the Earth, it means that for two clocks that are separated vertically by 10 centimeters, the higher clock runs at a rate which is 1 part in 10 to the 17 faster than the lower clock. And in fact, we're down now below, precision below this. So this is the kind of things we have to worry about. Just so it's kind of a cheesy demonstration of this, we have 2 of these aluminum clocks. They're certainly not portable, which I'm trying to sell here. But anyway, they're on these optical tables. So the reason we called this portable is in this simple demonstration, you can see in this picture, we put some jacks underneath the table. So James Chow here has first made a comparison measurement, and then he's raised the table by, in this case, 33 centimeters, and we predict to see a shift of this size, and within our error bars we see this shift, and so this is not at all a precision measurement. There's certainly been more precise measurements done of this gravitational potential redshift. But what's interesting is what it means is now, as we reach these very high precisions in the clocks, it turns out that the only way we can do precise comparisons is the clocks have to be in the same location. And the reason for that is, although for example, we can compare our clocks to clocks at sea level, the fiber links are precise enough, but the problem is we don't know the difference in the gravitational potential, say from Boulder down to sea level, and it's aggravated a bit in Boulder because of the mountains there. But the uncertainty of this gravitational potential expressed as a height in Boulder is about 30 centimeters. So to me it was kind of disappointing. Spending all my whole career on trying to make better clocks, and now I just have we only have a yardstick, even with these very precise figures. But the idea is, of course, to turn this around. Let's not be negative about this. It's a way potentially to perform geodesy in the future. So I'm going to summarize now, but again, I want to say that this work is due to a lot of people. I showed you earlier these guys over here on the right, and John Bollinger joined us not long after that earlier picture I showed you, and more recently Till Rosenband and Dede Leibfried have joined us. Chris Monroe was, as I mentioned, in a group from 92 to 2000, but of course, in addition to these guys, over the years we've had more than 100 students, postdoc, and visitors that really did all the work. And I must say I've been very lucky in being at NIST. We've had very good institutional support. I mentioned my first boss when I arrived there, and Catherine Gebbe, who's our laboratory director, two steps above me. One measure of her success, I would say, is that after Eric Cornell and Bill Phillips and Jan Hall, I'm the fourth recipient of the prize under her directorship. So she's done a fantastic job. And of course, I have to thank all the agencies at the same time for the support over the years. So let me say a little bit about the ceremony. It really was a surreal event for me, and certainly most physicists. This is a very extremely special experience, and this was the venue for the award ceremony. So over here on the right-hand side is the royal family, and there were 9 laureates across the various disciplines this year, and everything is just over the top, very, very fancy. And so after this award ceremony, this occurs in early December every year. After the award ceremony, the king and queen had a few people over for dinner. So one thing you kind of realize after you go there is that each laureate, unfortunately, we were only allowed to bring 10 guests to these major events, and certainly we would like 12 guests, but we would certainly like to bring a lot more if we could. But you do a rough calculation, that's probably about 100 people. Well, there was 1,200 people at this dinner, and so you clearly appreciate this is for Swedish society, Swedish officialdom as well. It's a very big deal for Sweden, and so they obviously preserve this in a nice way. But anyway, it was certainly a wonderful experience. I have a lot of other fun stories to tell about the events here. But let me conclude by saying Serge Hiroshio, I shared the award with. What's been really nice is, of course, I've known his work for almost my whole career. I became friends with him about 25 years ago, and in the meantime, our wives have also become good friends. So it's a special pleasure to have received the award with him. And so, with that, thank you.